It turns out that gases have fairly simple behavior. You can measure a few of the properties of gases and relate them to other properties without too much trouble. Gases behave very simply because the molecules of gases don't really interact with each other much unless they're directly colliding with each other. That makes their properties fairly simple. In fact, there's 4 properties that can be used to describe the condition of a gas sample. We say the state of a gas sample. Now we're using the word state a little differently than we usually use it. Usually if I say a state of matter, I mean, is it solid, liquid, or gas? But here we're talking about the condition a sample is in, using a little laundry list of properties that we measure. And there's only 4 that you need. Volume is a pretty familiar property. The volume of a gas is the volume of a container, since it fills the container completely. And we use a capital V in equations when we're talking about volume. And what kind of units can it have? Well, you can have the SI unit would be cubic meters. But people can use other length units, cubed, too. You can talk about cubic feet in English, or you can talk about cubic centimeters, but that would be the SI base unit for volume. Amount of gas is another state variable, and we give it a symbol N. It's really moles. Moles of gas. So when we're talking about amount of gas, we're talking about moles of gas. Okay, so far so good. It turns out that these things are easy to relate. At 0 degrees Celsius, gases have a molar volume, which is V per mole, volume per mole, which is about 22.4 liters. Now liters is another volume unit that we're going to use so often that we might as well put that in our little table here. Meters cubed or liters, either one. But these two aren't independent of each other. If you're at that particular temperature, you're going to have about that volume. So that 22.4 liters per mole is the molar volume, the volume of a mole of a gas at 0 degrees. So that's an example of a simple relationship between two properties of the gas. Now, another property is temperature. This number isn't quite right at other temperatures. In fact, if you have a higher temperature, the gas expands a little bit, so it'll be a number a little bit more than this at a higher temperature than 0 degrees. We use a capital T in equations for temperature, and we're always going to use Kelvin for the temperature. Remember that if the problem gives you degrees Celsius, you have to convert it into kelvins if you're going to do gas law calculations later. For example, if you've got the temperature in degrees Celsius, you can add 273.15 to it to get the Kelvin temperature. For example, 25.00 degrees Celsius is going to be 298.15 kelvins. So anytime somebody throws you a temperature in degrees Celsius at you in this chapter, you're always going to just turn it into Kelvin. The last property is the one I want to talk about the longest. It's pressure. And we usually use a P for that. Now what are the units for pressure going to be? Well, we have to define pressure. It's force per unit area. So it isn't just force, it's force per unit area. For example, you sit on a nail, here's a nail or a thumbtack, there's a really small area there. And the force that you're going to bear down on that is going to be your weight. So your force is your weight, which is times acceleration due to gravity. When somebody says a weight, they're talking about this force. So this is a little high school physics here. G, this constant, is about 9.8 meters per second. So it's about that. If I put the mass in kilograms, I'm going to have, what? It's going to be kilograms times meters per second squared for force. And what are the units of area? The units of area are going to be, say, square meters. So this will be my SI base unit of pressure. We can clean this up a little bit. I mean, there's a meters there and a meters there. Now notice I'm using the symbol M two different ways here. Look at the context. Here it's a mass. Here I'm talking about meters. So those things are different. All right. Now, if I clean this up a little bit, I could write that doesn't really help me though. I could also recognize that this is called a Newton. That clump of units for force is the SI base unit for force. So the SI base unit for pressure is a Newton, a force unit, divided by meters squared, which is an area unit. And this is still a little too complicated. Let's hide all the unnecessary detail. I'm going to make a new unit, PA. It's a pascal. So I'm going to say a pascal, a PA, is a Newton per square meter. Or you could write the unit like this. So it's a pascal that is our SI base unit. Now there are several other pressure units that people use that we'll talk about in a minute. But let's play around with the idea of a pascal. Suppose I have got an elephant with a mass of let's say 2,000 kilograms. And elephants have big feet. Their foot area is going to be 5,000 square centimeters, let's say. Let's figure out how many pascals of pressure the elephant exerts on its feet. Okay, the pressure, P, is going to be the force, which is the mass times the acceleration due to gravity, divided by the area. Now, I've got an area of 5,000 square centimeters. This calculation as it is, if I plug into my calculator 2,000 times 9.8 divided by 5,000, I'm not going to get an answer that makes a lot of sense because I have got meters here and I've got square centimeters down here. I need to have my length units consistent through this whole thing. It will be better if I put the area units in the denominator into square meters. So I'm going to do a conversion down here in place where I get rid of the square centimeters and put square meters there. And remember, we did this way back in the beginning of the course. it's going to be what? 1 square centimeter is going to be 10 to the minus 2 squared meters squared. So I could pick up my calculator at this point and say 2,000 times 9.8 divided by 5,000 divided by 10 to the minus 2 squared is going to be what the pressure is going to be. The units will all come out right. Notice that the units that I have here are the same as the units that I wrote here. So that will be whatever that is in pascals. Your first problem is just like this problem.